Let the day slowly fade away, and feel your body coming to rest. This is your path into a world of stillness, starlight, and gentle dreaming. Take a deep breath, and sink softly into the night. Your journey begins now. Close your eyes and imagine walking through a forest as summer fades. The air has changed, there's a crispness to it now, a gentle coolness that wasn't there just weeks ago. The light falls differently through the trees, golden and slanted, casting long shadows across paths carpeted with leaves. This is autumn, nature's most painterly season, when the world transforms in ways both subtle and spectacular. Let us wander together through this season of change, discovering the quiet miracles happening all around us. The timing is exquisite. Trees sense the changing length of daylight through specialized proteins in their leaves, beginning their transformation at precisely the right moment for their species and location. Before those leaves fall, the tree performs one final act of resourcefulness. It withdraws valuable nutrients, nitrogen, phosphorus, and other minerals, from the leaves and stores them in its trunk and roots for the winter ahead. A special layer of cells forms at the base of each leaf stem, called the abscission layer, which gradually seals off the leaf from the tree's vascular system. This process is so efficient that trees reclaim up to 50% of the nutrients from their leaves before letting them go. Nothing in nature is wasted. When the connection is finally severed, the leaf drifts down, sometimes spinning like a tiny helicopter, sometimes tumbling in the breeze, each one taking its own unhurried path to the forest floor. Those fallen leaves become a world unto themselves. A single leaf, which may seem like simple debris to us, provides habitat and food for countless creatures. Earthworms pull leaves underground, shredding them and mixing them with soil. Millipedes, springtails, and mites break them down further. Fungi send out delicate threads, decomposing the tough cellulose. By spring, that leaf will have been transformed into rich humus, the dark, crumbly layer of topsoil that nourishes new growth. An oak leaf takes about a year to fully decompose, while a maple leaf may break down in only 6 months. The forest is constantly recycling itself, death becoming the foundation for new life. Animals throughout the forest read autumn's signals and respond with ancient instincts. Squirrels enter a period of intense activity called scatter hoarding, hiding thousands of acorns, nuts, and seeds across their territory. A single gray squirrel may cache up to 10,000 nuts in a season, burying them in hundreds of different locations. Their spatial memory is extraordinary. They can remember where they've hidden food months later, even beneath a blanket of snow. But they don't find everything. The forgotten seeds, buried in perfect planting conditions, will sprout in spring. In this way, squirrels unknowingly become gardeners, planting oak forests one forgotten acorn at a time. Birds, too, transform in autumn. Many species that filled the summer air with song are now preparing for journeys of thousands of miles. Before migration, birds enter a state called hyperphagia, eating voraciously to build up fat reserves that will fuel their flight. A small warbler, weighing less than an ounce, may nearly double its body weight. Some birds, like the Arctic tern, will travel from the Arctic to Antarctic and back each year, a round trip of over 40,000 miles. They navigate using the Earth's magnetic field, the position of the sun and stars, and landmarks memorized from previous journeys. On autumn nights, if you listen carefully, you might hear their calls overhead as they travel through darkness, staying in contact with their flock. As the insects of summer fade, autumn brings its own special emergence. Monarch butterflies, those delicate orange and black wanderers, begin one of nature's most mysterious journeys. Unlike most butterflies that live only weeks, the generation born in late summer, called the supergeneration, can live up to 8 months. These remarkable insects will fly up to 3,000 miles from North America to specific mountain forests in Mexico, traveling to trees their ancestors visited but they themselves have never seen. Scientists still don't fully understand how they navigate to these exact locations, generation after generation. It's as if the route is written somewhere in their being, a map passed down through genes and instinct. The autumn forest floor becomes a gallery of fungi, mushrooms pushing up through leaf litter in extraordinary forms and colors. These are merely the fruiting bodies of vast networks of mycelium spreading through the soil below, sometimes covering acres. The honey mushroom fungus in Oregon's Blue Mountains is estimated to be over 2,400 years old and covers more than 2,000 acres, making it possibly the largest living organism on Earth. Fungi play a crucial role in autumn's ecology, decomposing organic matter and forming partnerships with tree roots called mycorrhizae, where they exchange nutrients with their plant partners. In autumn, as trees focus on storing resources, these fungal networks become highways for transferring nutrients throughout the forest. The angle of autumn sunlight creates moments of particular beauty. As the earth tilts away from the sun, light must pass through more of the atmosphere to reach us, scattering blue wavelengths and allowing reds and oranges to dominate. This is why autumn sunrises and sunsets seem especially vivid, painting the sky in shades of amber and crimson. The same light filtering through colored leaves creates a warm, golden quality that photographers call the golden hour, though in autumn, this magical light seems to linger throughout the day. Morning mists rise from lakes and rivers where water temperatures remain warmer than the cooling air, creating ethereal scenes where the boundary between earth and sky seems to dissolve. Even as the visible world seems to slow down, beneath the soil, autumn is a time of quiet activity. Tree roots continue growing, taking advantage of warm soil and autumn rains to extend their reach before winters freeze. Bulbs of spring flowers, tulips, daffodils, crocuses, are already forming beneath the earth, developing the beginnings of next year's blooms. They need autumn's chill to trigger their spring emergence, a process called vernalization. The seeds of countless plants are also preparing for dormancy, developing hard coats that will protect them through winter's cold, waiting for spring's warmth to signal their awakening. As you settle deeper into rest, imagine yourself as part of this great seasonal shift, the forests breathing out their leaves, the creatures preparing for journeys or long sleeps, the light growing softer and more golden. Autumn teaches us about transformation, about letting go, about the beauty in transitions. Nature doesn't resist the change, it flows with it, trusting in the cycle that has repeated since the first forests grew. The cooling temperatures of autumn trigger remarkable changes in the insects that remain active. Woolly bear caterpillars, those fuzzy brown and black creatures often seen crossing paths and roads, are searching for protected places to spend the winter. According to folklore, the width of their brown bands predicts the severity of the coming winter, though scientists tell us the bands actually indicate the caterpillar's age and how well it fed during summer. Still, these small wanderers carry their own magic. They survive winter by producing a cryoprotectant, a natural antifreeze in their bodies, that prevents ice crystals from forming in their cells. Frozen solid, their hearts stopped, they wait in suspended animation until spring's warmth revives them. Autumn rain has its own unique character, different from summer's thunderstorms or spring's gentle showers. These are steady, soaking rains that penetrate deep into the soil, replenishing groundwater reserves depleted by summer's heat. The smell we associate with autumn rain, that earthy, almost sweet scent, is called petrichor. It's created when rain strikes dry soil, releasing oils that plants have secreted during dry periods, along with a compound called geosmin produced by soil bacteria. This scent actually serves a purpose. It signals to plants that moisture has arrived, triggering various growth processes. For many seeds lying dormant in the soil, autumn rain is the signal they need to prepare for germination, swelling with moisture and beginning the biochemical changes that will culminate in spring's sprouting. Deer, elk, and moose enter their breeding season, the rut, as autumn progresses. The cooling temperatures and changing light trigger hormonal changes that transform normally peaceful male deer into competing rivals. Bull elk produce their haunting bugling calls that echo through mountain valleys, a sound that can carry for miles on crisp autumn air. These calls serve multiple purposes: attracting females, warning other males, and announcing their fitness as mates. Males have spent the summer growing impressive antlers, which reach their full size by autumn. These antlers aren't permanent structures but rather grow anew each year, making them one of the fastest growing tissues in the animal kingdom. After the breeding season ends, the antlers will be shed, their calcium and minerals recycled by mice, porcupines, and other animals that gnaw on them. The ponds and wetlands of autumn host their own quiet dramas. Frogs and turtles begin preparing for winter in ways that seem almost miraculous. Wood frogs, found throughout North America, survive winter by allowing up to 70% of their body water to freeze solid. Their hearts stop beating, their breathing ceases, and ice crystals form in the spaces around their cells. Like the woolly bear caterpillar, they produce glucose and other compounds that protect their organs from freezing damage. When spring arrives, they thaw from the inside out, their hearts somehow restarting, their breathing resuming, as if they're being resurrected. Painted turtles, meanwhile, sink to the bottom of ponds where they'll spend winter in a state of deep dormancy, absorbing oxygen directly through their skin from the water around them. The autumn sky becomes a theater for one of nature's most mesmerizing displays, murmurations of starlings. These massive flocks, sometimes numbering in the hundreds of thousands, create flowing, shape-shifting patterns across the evening sky before roosting. Each bird follows simple rules: stay close to your neighbors, match their speed, avoid collisions, yet together they create complex, seemingly choreographed movements that ripple through the flock in waves. Scientists believe these spectacular displays serve multiple purposes, confusing predators like hawks and falcons, sharing information about food sources, and providing warmth through the sheer number of birds roosting together. Watching a murmuration is like witnessing a single organism made of many parts, moving with fluid grace across the dimming autumn light. Trees prepare for winter in ways beyond dropping their leaves. Deciduous trees must protect themselves from the damage that freezing and thawing can cause. They begin moving water out of their cells and into the spaces between cells, where ice formation won't rupture delicate cellular structures. They also produce special proteins that act as antifreeze, lowering the freezing point of their sap. The cambium layer, the living tissue just beneath the bark where growth occurs, enters dormancy, slowing its metabolic processes to near stillness. Evergreen trees, like pines and spruces, coat their needles with a waxy substance that prevents water loss during winter when frozen ground makes it impossible for roots to draw up moisture. Their needles are also designed to shed snow, with flexible branches that bend under weight rather than breaking. Autumn is harvest time not just for humans, but for countless creatures. Black bears enter a state of hyperphagia similar to migrating birds, but far more extreme. They may spend up to 20 hours a day eating, consuming up to 20,000 calories daily, the equivalent of about 40 hamburgers. They feast on berries, nuts, insects, and anything else they can find, building the fat reserves that will sustain them through winter hibernation. A bear might gain several pounds every single day during this period. Their bodies undergo remarkable changes. Their metabolism shifts, allowing them to digest food more efficiently and convert it to fat. Come winter, they'll retreat to their dens and spend months without eating, drinking, urinating, or defecating, surviving entirely on stored fat while their heart rate drops from 50 beats per minute to just 8. The spider webs we notice more frequently in autumn have been there all along, we simply see them better now. Cool autumn mornings produce heavy dew, and these water droplets cling to the silk strands, making them visible and transforming them into jeweled nets that sparkle in the early light. Autumn is actually peak web building season for many spider species. They've grown to their full size after a summer of hunting and are now producing egg sacs that will survive the winter. The silk they spin is one of nature's marvels, stronger than steel of the same diameter, incredibly elastic, and produced from liquid protein that solidifies instantly upon contact with air. Some species of spiders even engage in ballooning in autumn, releasing silk strands that catch the wind and carry them, sometimes for hundreds of miles, to new territories. On calm autumn days, these silk strands fill the air in phenomenon sometimes called gossamer, turning fields into seas of floating silver threads. As autumn deepens, the night sky itself changes. The constellations of summer, the bright stars of the summer triangle, begin their descent in the west, while autumn's own celestial markers rise in the east. The great square of Pegasus dominates the autumn sky, along with the graceful chains of stars forming Andromeda. The Milky Way, our galaxy viewed edge-on, arcs overhead with particular clarity in autumn's crisp, dry air, often less humid than summer's hazy skies. This is also the season when the Orionid meteor shower peaks, debris from Halley's Comet burning up in Earth's atmosphere, creating streaks of light across October skies. Ancient peoples marked their calendars by these celestial changes, knowing that when certain stars appeared on the horizon at sunset, it was time to harvest, to prepare, to gather close for the coming cold. Let yourself drift with these images, webs jeweled with morning dew, flocks of birds painting patterns across twilight, bears drowsy with the weight of approaching sleep. Autumn reminds us that change is natural, that preparation is wisdom, that beauty often appears in the act of letting go. The autumn garden, even as it fades, continues to provide. Many plants produce their most valuable offerings now, seeds packed with concentrated nutrition that will feed countless creatures through winter. Sunflowers bow their heavy heads, each disc filled with hundreds of seeds arranged in mesmerizing spirals that follow the Fibonacci sequence, a mathematical pattern repeated throughout nature. Goldfinches, their summer brightness fading to olive brown, gather at these seed heads, their cheerful calls accompanying the sound of their feeding. These late-season seeds are designed for dispersal and survival. Some have hooks or barbs that catch on fur and feathers, traveling far from their parent plant. Others have feathery plumes that catch the wind, sailing through autumn air like tiny paratroopers seeking new ground. Beneath the leaf litter, an entire civilization exists that most of us never see. Autumn is prime time for this hidden world. The decomposers, bacteria, fungi, protozoa, nematodes, and countless tiny arthropods, work in concert to break down organic matter. A single handful of healthy forest soil contains more living organisms than there are people on Earth. These microscopic workers are responsible for creating the rich, dark humus that makes soil fertile. The process is complex and beautiful in its efficiency. Fungi break down tough plant fibers, bacteria decompose simpler compounds, and larger creatures like springtails and mites shred material into smaller pieces. The result is a slow-motion transformation where fallen leaves become the foundation for next year's growth, where death quite literally feeds life. Rivers and streams undergo their own autumn transformations. As water temperatures cool, dissolved oxygen levels increase. Cold water holds more oxygen than warm. This triggers increased activity among trout and salmon, which thrive in oxygen-rich water. For Pacific salmon, autumn is the culmination of their entire existence. Having spent years at sea, they navigate back to the exact streams where they were born, swimming against powerful currents, leaping up waterfalls, driven by an instinct so powerful that they stop eating entirely, using only their stored energy for this final journey. When they reach their spawning grounds, they lay their eggs in gravel beds, then die, their bodies becoming food for bears, eagles, and the forest itself. The nutrients from their ocean-fed bodies fertilize streamside plants and enrich the ecosystem that will nourish their offspring. It's a cycle of sacrifice and renewal that has repeated for millions of years. The changing quality of autumn light affects not just what we see, but what plants experience. Shorter days trigger photoperiodism in many plant species, the biological response to the length of day and night. Chrysanthemums bloom in autumn specifically because they're short-day plants, requiring long periods of darkness to produce flowers. This same mechanism causes many plants to enter dormancy. The phytochrome proteins in plant cells act like tiny light meters, measuring precisely how many hours of darkness occur in each 24-hour period. When darkness exceeds a certain threshold, different for each species, it triggers cascading biochemical changes, growth slows, buds form protective scales, and plants prepare for winter's arrival. This ancient timing mechanism is so precise that plants can detect even small changes in day length, responding to the steady march of seasons with perfect reliability. Bats, those misunderstood creatures of twilight, face critical decisions as autumn arrives. Insect-eating bats in temperate regions must either migrate to warmer climates or find caves and structures where they can hibernate. Before hibernating, they feed intensively, building fat reserves that must last them through months of dormancy. During hibernation, their body temperature drops dramatically, sometimes to just above freezing, and their heart rate slows from over 1,000 beats per minute to fewer than 25. They breathe only once or twice per hour. This state of torpor is so deep that disturbing a hibernating bat can be fatal, as the energy required to wake up and warm their body depletes precious fat reserves they need to survive until spring. A single unnecessary awakening might mean the difference between surviving winter and starving before insects return. The forests of autumn ring with sounds we might not immediately recognize. Acorns and other nuts, ripened and released, rain down through the branches, creating a percussion that fills the woodland air. This masting phenomenon, when trees produce enormous quantities of seeds all at once, doesn't happen every year. Many tree species synchronize their heavy seed production on cycles of 2 to 5 years. Scientists believe this evolved as a survival strategy. By flooding the environment with more seeds than animals can possibly eat, trees ensure that at least some will survive to germinate. In non-masting years, seed-eaters like squirrels, jays, and mice maintain stable populations. But in masting years, the sheer abundance creates a surplus that guarantees some seeds escape predation. It's a strategy of overwhelming generosity that benefits both trees and the animals that depend on them. Autumn winds carry with them an invisible cargo of seeds, spores, and pollen. Ragweed releases billions of pollen grains into autumn air. Each plant can produce up to 1 billion grains in a season. These microscopic particles, designed to travel on the wind, can journey hundreds of miles from their source. But it's not just allergenic pollen on the breeze. Seeds of maples, elms, and ash trees helicopter down in spinning flight, their wing-like structures designed through millions of years of evolution to maximize dispersal distance. Dandelion seeds, though more common in spring, still float through autumn air on their feathery parachutes. Milkweed pods split open, releasing seeds attached to silky threads that catch the slightest breeze. The autumn air is thick with potential, with the promise of future forests, meadows, and gardens, if only the seeds can find suitable ground before winter arrives. The soil itself undergoes a transformation in autumn. As temperatures cool and moisture increases, earthworm activity reaches a seasonal peak. These tireless workers, often called ecosystem engineers, process organic matter in ways that benefit countless other organisms. An earthworm eats its own weight in soil and organic matter each day, grinding it in their gizzard and excreting it as castings, small mounds of processed soil that are remarkably fertile, containing 5 times more nitrogen, 7 times more phosphorus, and 11 times more potassium than the surrounding soil. A healthy acre of land might contain 1 million earthworms, and over the course of a year, they can move and process 15 tons of soil. Their tunnels aerate the earth, allowing water and air to penetrate deep into the ground, creating passages that plant roots will follow come spring. As autumn progresses, certain trees and shrubs offer one final gift before winter, berries and fruits that ripen precisely when migrating birds need them most. The relationship between fruiting plants and birds is one of nature's most elegant partnerships. Plants wrap their seeds in nutritious, colorful packages that birds can spot easily. Birds eat the fruit, digest the flesh, and deposit the seeds, often miles away, in a convenient package of fertilizer. Some berries, like those of the dogwood and viburnum, are especially high in fat, providing concentrated energy for birds preparing for migration or facing winter scarcity. The bright red berries of mountain ash, the deep purple of pokeweed, the translucent white of snowberry, each has evolved to appeal to specific bird species, creating partnerships that benefit both plant and animal, ensuring that seeds travel far from parent plants and that birds have the fuel they need for survival. Rest now in these images of preparation and partnership, earthworms tunneling through cooling soil, seeds spinning through golden light, salmon swimming home against impossible currents. Autumn shows us that ending and beginning are not opposites but partners in the eternal dance of seasons. The marshes and wetlands of autumn become stages for one of nature's most spectacular gatherings. Sandhill cranes, those ancient birds whose fossil records stretch back millions of years, congregate by the tens of thousands in specific staging areas during their autumn migration. The Platte River in Nebraska, for instance, hosts over 500,000 cranes each autumn. Their calls, a prehistoric rattling that carries for miles, fill the air at dawn and dusk as they rise from and return to roosting sites. These gatherings serve crucial purposes: safety in numbers from predators, social learning where young birds absorb migration routes and behavior from elders, and opportunities to feed intensively in preparation for long flights ahead. To witness such a gathering is to see something that has repeated for eons, a ritual older than human civilization. Autumn brings a particular urgency to the amphibian world. Frogs, toads, and salamanders must find their overwintering sites before temperatures drop too far. Different species have evolved remarkably different strategies. American toads burrow backward into loose soil, digging down below the frost line where they'll remain dormant until spring. Bullfrogs settle into the muddy bottoms of ponds, their metabolism slowing dramatically but never quite stopping. They remain somewhat active throughout winter. Salamanders seek out rotting logs, spaces beneath rocks, or abandoned burrows. The critical factor for all of them is finding a place where they won't freeze solid, yet where temperatures remain cool enough to keep their dormant metabolism from depleting their energy reserves before spring. It's a delicate balance, and those who choose poorly may not survive. The autumn forest canopy creates a unique microclimate for the creatures that dwell within it. As leaves fall, the remaining structure, bare branches interlacing against the sky, becomes a highway and home for animals adapting to the season's changes. Gray squirrels build leaf nests called drays high in the branches, weaving together leaves and twigs into waterproof structures lined with soft materials like moss, grass, and shredded bark. These nests can be 2 feet in diameter and are engineered with multiple exits, an adaptation to evade predators. A single squirrel may maintain several drays throughout its territory, moving between them as weather, food sources, and predator pressure dictate. On cold nights, multiple squirrels sometimes share a single dray for warmth, their usual territorial behavior temporarily suspended in favor of survival. Autumn rain creates temporary pools and puddles that become microscopic worlds. These ephemeral water bodies host fairy shrimp eggs that have lain dormant in dry soil, sometimes for years, waiting for exactly these conditions. Within days of water appearing, the eggs hatch and develop into delicate, translucent creatures that swim upside down, filtering microorganisms from the water. They live only weeks, but in that time they grow, reproduce, and lay eggs that will survive the coming winter, the next dry season, and perhaps many more years until conditions are right again. It's a strategy of patience and opportunism, of life compressed into brief windows of favorable conditions. These temporary pools also provide drinking water for countless insects, birds, and mammals, creating gathering places in the autumn landscape. The phenomenon of leaf peeping, traveling to view autumn foliage, has a scientific basis beyond simple aesthetics. The brilliant colors we see represent real chemical events. Red and purple anthocyanins are actually produced by trees in autumn, not just revealed like the yellows and oranges. Scientists believe trees produce these compounds to protect leaves during the nutrient withdrawal process, acting as a sunscreen while the tree reclaims valuable resources. The intensity of autumn color depends on specific weather conditions. Warm, sunny days produce sugars in leaves, while cool nights prevent these sugars from leaving the leaf. This trapped sugar triggers anthocyanin production, creating the most vibrant reds and purples. Drought stress can dull colors or cause leaves to drop prematurely, while ideal conditions, warm days, cool nights, adequate moisture, create the spectacular displays that draw admirers from around the world. Beneath the bark of dying and dead trees, autumn triggers a surge of activity. Bark beetles, dormant through summer's heat, become active as temperatures cool. These tiny engineers bore through bark, creating elaborate tunnel systems where they lay their eggs. While often portrayed as tree killers, bark beetles primarily target trees already weakened by drought, disease, or age. They're part of the forest's natural recycling system. The galleries they create allow fungi and bacteria to enter the wood, beginning the decomposition process. Woodpeckers follow, excavating the beetles and their larvae, creating cavities that will later house owls, squirrels, and countless other species. A single dead tree might support over 1,000 different species over its decades-long decomposition. What appears dead to us is actually teeming with life, transformed from living tree into a complex apartment building for the forest community. The night air of autumn carries sounds that differ from any other season. As temperatures drop, sound waves travel differently, cooler, denser air carries sound farther and more clearly than summer's heat. This is why autumn nights seem particularly quiet, yet also why distant sounds travel with unusual clarity. The chirping of crickets slows as temperatures drop. You can actually estimate the temperature by counting cricket chirps. Count the number of chirps in 14 seconds and add 40 to get the temperature in Fahrenheit. This works because crickets are cold-blooded, and their metabolism, including the muscle contractions that produce chirps, slows predictably with temperature. The last cricket songs of autumn, slowing and eventually stopping as frost arrives, mark the final notes of the warm season symphony. Autumn's falling leaves create what ecologists call nutrient pulses, sudden availability of resources that triggers cascading effects through the ecosystem. When leaves hit the ground, they're not uniform in their nutritional value. Some species, like ash and basswood, decompose quickly and release nutrients rapidly. Others, like oak and beech, contain more tannins and decompose slowly, releasing nutrients gradually over months or even years. This variety creates a complex, layered release of nitrogen, phosphorus, and other minerals that different organisms can exploit at different times. The forest floor becomes a temporal buffet, with early decomposers getting different resources than late-season processors. This timing ensures that nutrients don't simply wash away in autumn rains but are captured, processed, and held in the ecosystem through multiple pathways and timescales. The behavior of domestic animals reflects ancient wild instincts responding to autumn's changes. Horses grow thick winter coats triggered not by temperature but by the shortening photoperiod. They begin developing their winter fur in August, long before cold arrives. Dogs often become more playful and energetic as temperatures cool, harking back to their wolf ancestry when autumn meant prime hunting season. Even house cats may exhibit increased activity, their predatory instincts stirred by the movement of mice and other small mammals seeking shelter. These domesticated companions carry within them the same seasonal rhythms that guide wild creatures, responding to cues embedded in their biology over millions of years of evolution, reminders that they too are part of nature's great cycle. Feel yourself settling deeper into comfort, like a bear finding its den, like seeds nestling into soil, like trees drawing their life force inward. Autumn teaches us the wisdom of preparation, the beauty of transition, the trust required to let go and await renewal. The grasses of autumn meadows hold their own quiet beauty. While showier plants fade, grasses come into their glory, their seed heads catching light, bending gracefully under their own weight, creating waves of golden movement across fields. These grasses are performing essential work. Their extensive root systems, which can extend 6 feet or more into the soil, are actively growing even as the visible parts turn brown. Prairie grasses store carbohydrates in their roots throughout autumn, building reserves that will fuel explosive spring growth. A single big bluestem plant might have over 300 miles of roots spreading through the soil. When these roots die and decompose, they create channels in the earth, improve soil structure, and add organic matter deep underground. The prairies of North America were built, over thousands of years, by these humble grasses and their intricate root systems. Autumn fog creates ephemeral landscapes that transform the familiar into something dreamlike. These fogs form when warm, moist air meets cooling ground, causing water vapor to condense into tiny droplets suspended in the air. Autumn is prime fog season in many regions because temperature differences between day and night are at their greatest. Morning fog in valleys can be so thick it seems solid, yet it's composed of droplets so small that a cubic meter of dense fog contains less than half a gram of water. These fog events are crucial for certain ecosystems. In coastal forests, fog drip can contribute more moisture than rainfall, with trees combing water droplets from the air. Mosses, lichens, and ferns absorb moisture directly from fog, and many insects and spiders drink from droplets that condense on their webs and bodies. What appears to us as obscured visibility is, to many organisms, a drink in a dry season. The hedgerows and fence lines of autumn become corridors of concentrated life. These linear habitats, often the last semi-wild spaces in agricultural landscapes, support remarkable biodiversity. Hawthorn bushes heavy with red haws, wild roses displaying scarlet hips, blackberry canes with a few last dried fruits, these provide food and shelter for countless species. Small mammals like voles and shrews create runways beneath the tangled vegetation, hunting for seeds and insects. Wrens and sparrows glean the last insects from bark and dried stems. Hawks perch on fence posts, scanning for the movement of prey below. These edge habitats, where field meets woodland or meadow meets forest, create what ecologists call edge effects, increased diversity and abundance of life where two ecosystems meet. In autumn, when resources grow scarce, these concentrated corridors become lifelines for survival. The chemistry of autumn scents reveals complex ecological relationships. The distinctive smell of autumn, beyond petrichor, comes from compounds released by decomposing leaves. As fungi break down lignin and cellulose, they release volatile organic compounds with names like geosmin and 2-methylisoborneol. Our human noses are extraordinarily sensitive to these compounds. We can detect geosmin at concentrations as low as 5 parts per trillion, lower than a shark can detect blood. This sensitivity likely evolved because these scents indicated good soil for our ancestors' crops, or locations where edible fungi might be found. Animals too respond to autumn scents. Deer can smell acorns hidden beneath leaves, bears can detect ripening nuts from remarkable distances, and truffle-hunting pigs respond to compounds released by underground fungi that mimic the scent of pig pheromones, an accidental similarity that humans have exploited for centuries. The ponds and lakes of late autumn undergo a phenomenon called turnover that's invisible to the eye but crucial for aquatic life. During summer, lakes stratify into layers, warm water floats on top of cold water, with little mixing between them. As autumn cools surface water, it becomes denser and eventually sinks, causing the entire water column to mix. This turnover redistributes oxygen throughout the lake and brings nutrients from the depths to the surface. It's a reset button for the aquatic ecosystem, preparing it for winter's ice cover. Fish respond to this change, often feeding actively during turnover as nutrients trigger plankton blooms. The mixing can temporarily cloud the water as sediments rise from the depths, but this murkiness signals renewal, the lake breathing deeply before winter's stillness arrives. Owls become more vocal in autumn, their calls echoing through the cooling nights. While often associated with courtship in late winter, many owl species also establish or reinforce their territories in autumn. Great horned owls, barred owls, and screech owls all increase their calling in autumn months. These vocalizations serve multiple purposes: advertising territory, strengthening pair bonds, and teaching young owls, now independent but still learning, the calls of their species. The increased vocalization coincides with improved hunting conditions as vegetation dies back, making small mammals easier to spot and catch. Owls also grow fresh facial disc feathers in autumn, the specialized feathers that funnel sound to their asymmetrically placed ears, allowing them to pinpoint prey in complete darkness. These nocturnal hunters are preparing for winter, when their superior night vision and hearing give them advantages over daytime predators. The trees themselves communicate more urgently in autumn through their underground fungal networks, sometimes called the wood wide web. Through mycorrhizal connections, partnerships between fungal threads and tree roots, trees can transfer sugars, nitrogen, and chemical signals to one another. Research has shown that parent trees recognize their offspring and send them extra nutrients through these networks. In autumn, as older trees prepare for dormancy, they often transfer resources to younger trees, helping them survive their first winters. Douglas fir trees have been observed sending carbon to birch trees in autumn when the birch's leaves have fallen and they can't photosynthesize. In return, birches help firs in spring before fir needles are fully active. It's a mutualism that transcends species, a cooperation hidden beneath our feet, challenging our assumptions about trees as isolated individuals competing for resources. Autumn constellations wheel overhead with particular significance in the natural world. While we think of celestial navigation as primarily a spring and autumn migration phenomenon, it influences behavior throughout the season. Nocturnal animals including moths, beetles, and spiders use polarized moonlight and starlight for orientation. Dung beetles, remarkably, navigate by the Milky Way, the only insect known to use the galactic plane for orientation. Even on moonless autumn nights, they can roll their dung balls in straight lines by maintaining a fixed angle relative to that band of light crossing the sky. Migratory birds rely on star patterns learned during their first autumn, using circumpolar constellations that rotate around the North Star as their compass. Young birds raised in planetariums will orient their migration direction based on whatever artificial star pattern they're shown, demonstrating that this is learned behavior, knowledge passed down through observation during those first critical autumn nights. The last flowers of autumn, asters and goldenrods primarily, serve as critical refueling stations for the season's final insects. These late bloomers have evolved to exploit a niche. When competition for pollinators is reduced, they can offer nectar to the few insects still active and receive pollination services in return. Monarch butterflies, on their migration south, depend heavily on these late-blooming flowers. Bumblebee queens, the only members of their colonies that will survive winter, feed frantically on autumn asters, building the fat reserves they need to hibernate and found new colonies in spring. Honeybees make late-season honey from goldenrod nectar, storing these golden reserves for winter consumption. The relationship is so essential that the decline of native goldenrod and aster species in some regions has been linked to declining pollinator populations. These humble flowers, often dismissed as weeds, are keystones in the autumn ecosystem, bridges between summer's abundance and winter's scarcity. The moss on forest floors and tree trunks comes into its own in autumn. While often overlooked during showier seasons, moss thrives in autumn's cool, moist conditions. These primitive plants, unchanged for over 400 million years, lack true roots, absorbing water and nutrients directly through their leaves. Autumn's frequent rain and reduced evaporation create ideal conditions for moss growth and reproduction. They release spores from capsules held aloft on delicate stalks, tiny structures barely visible to the naked eye yet perfectly engineered to catch the wind. Moss provides crucial services to the forest. It holds moisture like a sponge, prevents soil erosion, and provides habitat for countless tiny invertebrates. A single cushion of moss might house hundreds of microscopic creatures, tardigrades, rotifers, nematodes, living in the thin film of water that clings to moss leaves, an entire universe existing in a handful of green. Coyotes, foxes, and other members of the dog family develop their thick winter coats in autumn through a process called molting. Unlike the spring molt where they shed their heavy winter fur, the autumn molt is a replacement process. Summer's lighter coat gradually falls out as denser, longer winter fur grows in. This new coat has two layers, a soft, insulating undercoat that traps warm air next to the skin, and longer guard hairs that repel water and wind. A fox's winter coat is so efficient that the animal doesn't need to increase its metabolic rate until temperatures drop below -70 degrees Fahrenheit. These canids also change their behavior in autumn, ranging more widely and caching food when they find surplus, burying eggs, small prey, and other items in scattered locations, creating hundreds of small pantries across their territory to draw upon when winter hunting becomes difficult. The streams and rivers of autumn carry falling leaves downstream, creating what aquatic ecologists call leaf packs, accumulations of leaves trapped against rocks, logs, and in slower pools. These leaf packs become foundation for aquatic food webs. Fungi and bacteria colonize the leaves within hours, softening them and making them more nutritious. Aquatic insects, caddisfly larvae, mayfly nymphs, and others, feed on these conditioned leaves, shredding them into progressively smaller pieces. Their waste products and the smallest leaf fragments feed filter feeders and collectors downstream. A single autumn's leaf fall supports the aquatic ecosystem throughout winter and into spring, providing food when little else is available. Some aquatic insects have evolved to time their life cycles specifically to exploit this autumn resource pulse, emerging as adults in late summer so their larvae can feed on the coming leaf fall. The phenomenon of harvest moon, the full moon nearest the autumn equinox, has real practical significance beyond folklore. For several nights around the harvest moon, the moon rises only about 20 to 30 minutes later each evening, rather than the usual 50 minutes. This happens because of the angle at which the moon's orbit intersects the horizon during autumn. For farmers working by moonlight to bring in crops before frost, these extra hours of light after sunset were genuinely valuable. But the harvest moon affects more than human agriculture. Nocturnal animals experience several nights of extended illumination, altering hunting and foraging patterns. Prey species become more cautious, while predators have extended hunting opportunities. Some moths and other night-flying insects reduce their activity during bright moonlit nights to avoid predation. The harvest moon is a reminder that celestial mechanics reach down to influence even the smallest creatures on Earth. Lichens, those partnership organisms of fungus and algae living as one, become more noticeable in autumn as leaves fall away from tree branches. These remarkable beings are among nature's most patient organisms, some individuals living for thousands of years, growing less than a millimeter per year. Autumn's moisture activates them after summer dormancy. When dry, lichens become brittle and dormant, but even a brief autumn rain transforms them within minutes. They absorb water, resume photosynthesis, and continue their imperceptibly slow growth. Lichens are extraordinarily sensitive to air pollution, particularly sulfur dioxide, and their presence or absence indicates air quality more reliably than many technological sensors. The diversity of lichen species in a forest tells ecologists about environmental conditions going back decades or even centuries. They're living archives, recording in their slow growth the history of the air around them. The garden spiders, orb weavers with their distinctive circular webs, reach their maximum size in autumn, having spent the entire growing season hunting and maturing. The females are now gravid with eggs, and their web building becomes especially impressive. A single garden spider might consume and rebuild her web every single night, eating the old silk to recycle its proteins. Silk production is metabolically expensive. Just before dawn, she spins a new web in the same location, a process taking about an hour. These autumn webs can span several feet and contain over 1,000 feet of silk. After mating in autumn, the female produces an egg sac containing hundreds of eggs, which she attaches to a protected location, under bark, in a rolled leaf, or in a building's eaves. She then dies with the first hard frost, her life's work complete, her offspring sealed safely in silk to emerge next spring. Trees demonstrate remarkable precision in their autumn leaf drop, a process called abscission that's far from random. Each tree species drops its leaves in a characteristic pattern and timing. Ash trees often lose all their leaves within a few days, sometimes overnight. Oak trees hold their leaves well into winter, a trait called marcescence. This variation isn't accidental, it reflects different evolutionary strategies. Early leaf drop allows trees to conserve water and avoid storm damage, but it also means giving up weeks of potential photosynthesis. Late leaf retention protects terminal buds from browsing deer and harsh weather. Some botanists suggest that oaks hold their leaves to drop them in spring, creating a sudden mulch that suppresses competing vegetation just as growing season begins. The exact timing depends on species, genetics, day length, temperature, and individual tree health, a complex calculation performed by each tree based on environmental signals and evolutionary heritage. Snakes, as autumn progresses, begin their journey toward hibernacula, the specific sites where they'll spend winter in dormancy. Many species are loyal to particular hibernation sites, returning to the same locations year after year, sometimes traveling several miles to reach them. These sites have specific requirements. They must be below the frost line but not so deep that snakes can't emerge in spring. They need proper humidity levels, and they must have entrance holes that don't flood. In some locations, hundreds or even thousands of snakes from multiple species will share a single suitable hibernaculum, creating massive autumn gatherings as snakes converge from across the landscape. Garter snakes in Manitoba form hibernating groups of tens of thousands. This communal denning provides thermal mass. the combined body heat of many snakes creates a slightly warmer microclimate, and may also serve social functions that scientists are still working to understand. The mushrooms fruiting in autumn forests include some of nature's most fascinating organisms. The honey mushroom, spreading through underground networks, uses bioluminescence. Its mycelium glows faintly in the dark, creating what has been called foxfire, a ghostly green light sometimes visible in rotting logs. The purpose of this glow remains debated, though some scientists suggest it attracts insects that help disperse spores. Autumn mushrooms have evolved diverse spore dispersal strategies. Some release spores that drift on air currents, others develop sticky spores that adhere to passing animals, and still others produce odors ranging from pleasant to putrid to attract specific dispersers. The stinkhorn mushroom produces a smell like rotting meat that attracts flies, which then carry spores on their feet. Each strategy represents millions of years of evolution, fungi solving the challenge of reproduction and dispersal without mobility, rooted to one spot yet managing to colonize vast territories. The Great Lakes and other large bodies of water undergo dramatic autumn changes that influence weather patterns for hundreds of miles around them. As air temperatures drop faster than water temperatures, these massive reservoirs of heat create what meteorologists call lake effect. Warm, moist air rising from the water surface meets cold air above, creating towering clouds. In autumn, before the lakes freeze, this phenomenon produces spectacular sunrises and sunsets, with clouds building and dissolving in endless processions. The temperature difference also creates localized weather. Shoreline communities may be 10 or 15 degrees warmer than areas just a few miles inland. This moderating effect extends the growing season in coastal areas, allowing fruit trees and grapevines to thrive where they otherwise couldn't. The lakes are thermal batteries, storing summer's warmth and slowly releasing it through autumn, softening the transition between seasons for all life in their vicinity. Beavers enter their most industrious season in autumn. Though known for industry year-round, their work intensifies as winter approaches. They repair and fortify their lodges, adding fresh mud and branches that will freeze solid, creating an impenetrable fortress against predators. They harvest trees with remarkable efficiency, felling aspens and willows, cutting them into transportable sections, and dragging them to their ponds. But they're not building, they're farming. Beavers store these branches underwater near their lodges, creating underwater food caches they'll access throughout winter when ice covers the pond. A single beaver family might store several tons of branches, enough to sustain them through months when the surface world is locked in ice. Their engineering transforms landscapes. Beaver ponds create wetlands that support countless other species, filter water, prevent erosion, and store groundwater. They're ecosystem architects, and autumn is their season of preparation. The plant world engages in chemical warfare that becomes apparent in autumn. Walnut trees, for instance, produce a compound called juglone in their roots, leaves, and nut husks. As autumn leaves fall and decompose, juglone leaches into the soil, inhibiting the growth of many competing plants, a strategy called allelopathy. Tomatoes, potatoes, and many other plants cannot grow near walnut trees. But some species have evolved resistance, even partnerships. Certain ferns and native wildflowers thrive beneath walnuts, having adapted to tolerate or even benefit from juglone's presence. This chemical communication extends throughout the plant kingdom. Sagebrush releases volatile compounds that inhibit nearby grass growth, preserving water for itself. Sunflowers produce toxins that prevent other sunflowers from germinating nearby. As autumn's decomposition processes release these chemicals, they shape which plants will emerge come spring, creating the distinctive plant communities we observe in different habitats. The phenomenon of false autumn, sometimes called Indian summer, occurs when a period of warm weather follows the first cold snap. This temperature roller coaster confuses neither the trees nor the animals, which respond to day length rather than temperature as their primary signal. But it does affect late-season insects dramatically. Butterflies that had become sluggish may briefly fly again. Crickets resume their songs. Flowers that began to wither produce a few final blooms. These warm reprieves are caused by high-pressure systems bringing warm air northward, creating brief returns to summer-like conditions. For migrating birds still traveling, these warm spells provide crucial feeding opportunities. For hibernating insects and amphibians, the warmth must be resisted. Emerging too early could be fatal. Many species have evolved multi-factor triggers for dormancy, requiring both temperature and photoperiod changes, protecting them from false signals that might lure them out prematurely. Autumn's cooling soil triggers the formation of frost flowers, ephemeral ice sculptures that form on certain plant stems during the first hard freezes. These delicate ribbons and curls of ice appear when water in plant stems freezes and expands, pushing out through cracks in the stem and immediately freezing into elaborate shapes. Frostweed and white crownbeard are particularly known for producing these formations. The ice emerges like white ribbons, sometimes creating structures several inches tall, twisted and curved in patterns that seem impossibly delicate. They last only until sunrise melts them, existing in a narrow window between night's cold and morning's warmth. These formations occur only once or twice per stem per season. Once the stem cracks, the pathway is broken. They're a reminder that autumn deals in ephemera, in beauty that exists for moments, in transformations that happen once and never repeat quite the same way. Owls and other raptors undergo their own autumn transformations, molting and replacing their flight feathers in a carefully sequenced pattern that never leaves them unable to fly. Unlike songbirds, which may molt all their feathers relatively quickly, raptors must maintain flight capability for hunting. They can't afford a period of flightlessness. They shed and replace feathers symmetrically, one or two at a time from each wing, maintaining balance and aerodynamics throughout the process. The new feathers emerging in autumn are fresh and pristine compared to the worn feathers of summer, improving their flight efficiency just as prey becomes more challenging to catch in winter's sparse landscape. The molt also includes facial disc feathers in owls, the specialized feathers that direct sound to their ears, ensuring their hearing remains acute for winter hunting in darkness and snow. The asters and goldenrods of autumn meadows create visual signals visible to insects but invisible to human eyes. Many flowers reflect ultraviolet light in patterns that guide pollinators to nectar sources, runways and bullseyes visible only to creatures that can see in UV spectrum. Bees, butterflies, and many other insects perceive these patterns, which direct them to the flower center where pollination occurs. As autumn progresses and insect populations dwindle, these remaining flowers compete intensely for the few remaining pollinators. Some late-season flowers have evolved stronger UV patterns, more concentrated nectar, or scents specifically attractive to autumn insects. The meadow we see with human eyes, pretty but straightforward, is to an insect eye a landscape of glowing signs and signals, a complex visual language advertising resources and directing traffic in ways we can only imagine. Chipmunks take a different approach to winter than their squirrel cousins. While squirrels remain active all winter, visiting their scattered food caches, chipmunks create centralized larders, underground chambers packed with seeds, nuts, and other food items. A single chipmunk may store several pounds of food in its burrow system. In autumn, they make dozens of trips daily, their cheek pouches bulging comically with seeds, racing against the calendar to accumulate sufficient stores. Unlike true hibernators, chipmunks enter a state of torpor but wake periodically throughout winter to eat from their pantries, maintain their nests, and eliminate waste. Their heart rate and body temperature drop significantly, but not as dramatically as bears or ground squirrels. This strategy, torpor with periodic waking, requires substantial food stores but allows for a faster spring emergence, as they don't need to rebuild depleted body tissues the way true hibernators do. The stars and planets shift position in the autumn sky, marking the passage of time with celestial precision. Jupiter and Saturn, the gas giants, are often prominently visible in autumn evenings, bright enough to cast faint shadows on moonless nights. These planets influenced human culture for millennia, but they also influence Earth in subtle ways. Their gravitational pull affects Earth's orbital variations over thousands of years, contributing to Ice Age cycles. The Pleiades star cluster, that small dipper of stars visible to the naked eye, rises in the eastern sky after sunset in autumn. Ancient cultures worldwide used the Pleiades as a calendar. Their heliacal rising, first appearance in the dawn sky, marked the beginning of various cultural new years, planting seasons, or harvest times. Even today, disconnected from agricultural cycles, we respond to these celestial changes with some ancient part of our awareness, sensing time's passage written in the stars. The very last insects of autumn include the autumn meadowhawk dragonflies, which can be seen flying on surprisingly cold days, even when frost covers the ground. These delicate-looking creatures have evolved remarkable cold tolerance, able to remain active in temperatures that immobilize other insects. They accomplish this through behavioral thermoregulation, basking in any available sunlight, vibrating their flight muscles to generate heat, and choosing sheltered microclimates where temperatures remain a few degrees warmer. These late-season dragonflies are often the only insects visible, patrolling over ponds and fields in solitary flight. They're hunting the very last mosquitoes and midges, which also possess cold tolerance. Watching an autumn meadowhawk on a cold October day, the only moving thing in a still landscape, feels like witnessing life's determination, its refusal to surrender even as the season demands it. Porcupines, those slow-moving, quill-covered rodents, prepare for winter by changing their diet and behavior in autumn. Throughout summer they feed on leaves, flowers, and green vegetation, but as these disappear, they shift to bark, stripping it from trees in distinctive patterns. They show preference for certain species, hemlock, pine, and aspen, and will actually girdle trees by eating bark all the way around, which kills the tree. While this seems destructive, it serves ecological purposes. Dead trees become habitat for cavity-nesting birds, insects, and fungi. Porcupines also develop thicker fur and add body fat in autumn, though they don't hibernate. They remain active throughout winter, resting in rock crevices, hollow logs, or tree cavities during the coldest days, emerging to feed when conditions allow. Their autumn preparations are modest compared to many animals. They're built for endurance rather than avoidance, accepting winter's challenges rather than fleeing or sleeping through them. The northern lights, aurora borealis, are often most visible during autumn and spring due to the orientation of Earth's magnetic field relative to the Sun during the equinoxes. During these periods, solar wind particles find easier entry into Earth's magnetosphere, creating increased auroral activity. Indigenous peoples across the northern latitudes have countless interpretations of the aurora, spirits dancing, ancestors playing games, omens of change. Animals respond to the aurora as well, though we're only beginning to understand how. Migratory birds may use auroral displays as navigation aids, and reindeer, which can see ultraviolet light, perceive the aurora differently than humans do, possibly seeing patterns and intensities invisible to us. The autumn aurora dances over landscapes preparing for winter, a reminder that Earth exists within a dynamic cosmic environment, constantly bathed in solar wind and particles from beyond. Seeds demonstrate extraordinary patience and specificity in their germination requirements, traits that become apparent in autumn as they settle into the soil. Many seeds require stratification, exposure to cold, moist conditions, before they'll germinate. This prevents them from sprouting in autumn only to be killed by winter. They must experience weeks or months of near-freezing temperatures, a counter that ensures they won't awaken until spring truly arrives. Other seeds require scarification. their seed coats must be scratched, burned, or digested before water can penetrate and germination begin. Some seeds can remain viable for decades or even centuries, waiting for conditions that may not arrive for generations. In this way, seeds are time travelers, packages of potential that can wait longer than the individual plants that produce them live, betting on futures they'll never see. The last butterflies of autumn often seek shelter in the same locations where they'll spend winter in diapause, a state of suspended development different from hibernation. Mourning cloaks, for instance, find loose bark, wood piles, or unheated buildings where they'll spend winter in a dormant state, neither growing nor aging, their development simply paused. They produce cryoprotectants, biological antifreeze, that prevents ice crystals from forming in their bodies. Come spring, they'll be among the first butterflies to emerge, flying on cold March days when snow still covers the ground. Question marks and Compton tortoiseshells employ similar strategies. These butterflies often live 9 months or more, extraordinary longevity for insects, spending most of that time in suspended animation. They experience two worlds, the dying autumn and the nascent spring, bookends of the cold season they sleep through. Autumn streams carry more than just fallen leaves, they transport the chemical signatures of the changing season. Tannins leaching from decomposing leaves tint the water amber or tea-colored, a phenomenon especially pronounced after heavy rains. These tannins, the same compounds that give tea and wine their astringency, are natural products of leaf decomposition. They lower water pH slightly, creating conditions that favor certain aquatic organisms over others. Brook trout and other fish that evolved in forested watersheds are adapted to these seasonal tannin pulses. The colored water also affects light penetration, changing the aquatic environment for photosynthetic algae and plants. This chemical transformation is temporary. By winter, much of the tannin will have been processed by bacteria or settled with sediments, but for weeks in autumn, the streams literally run with the essence of fallen leaves, the forest bleeding its colors into moving water. Autumn streams carry more than just fallen leaves, they transport the chemical signatures of the changing season. Tannins leaching from decomposing leaves tint the water amber or tea-colored, a phenomenon especially pronounced after heavy rains. These tannins, the same compounds that give tea and wine their astringency, are natural products of leaf decomposition. They lower water pH slightly, creating conditions that favor certain aquatic organisms over others. Brook trout and other fish that evolved in forested watersheds are adapted to these seasonal tannin pulses. The colored water also affects light penetration, changing the aquatic environment for photosynthetic algae and plants. This chemical transformation is temporary. By winter, much of the tannin will have been processed by bacteria or settled with sediments, but for weeks in autumn, the streams literally run with the essence of fallen leaves, the forest bleeding its colors into moving water. Box turtles, those terrestrial turtles with hinged shells that close completely, begin their winter preparations by seeking out forest floors with deep leaf litter. Unlike aquatic turtles that submerge in pond bottoms, box turtles dig into loose soil and cover themselves with leaves, creating insulated chambers where they'll spend winter in brumation, a reptilian form of dormancy. Their body temperature drops to match their surroundings, their metabolism slows to a fraction of its summer rate, and their heart may beat only once every 5 to 10 minutes. Box turtles can live over 100 years, meaning the oldest individuals have experienced more than 100 autumns, have buried themselves in leaves beneath trees that themselves have been replaced multiple generations. Their living archives of seasonal change, their long lives spanning transformations in forest composition, climate patterns, and landscape features that shift too slowly for shorter-lived observers to perceive. The phenomenon of autumn overturn in ponds creates brief windows of opportunity for organisms that specialize in these transitional moments. As surface water cools and sinks, nutrients from the bottom rise to the surface. Certain algae and plankton species bloom specifically during these overturn events, timing their life cycles to exploit the nutrient pulse. These blooms, in turn, attract specialized zooplankton that feed on these specific algae. Fish that have spent summer in deep, cool water move to shallows as temperature stratification breaks down, following prey that become newly accessible. Autumn overturn is a reset, a mixing, a brief period when the rigid vertical zones of summer, warm surface, cool depths, dissolve into uniformity before winter's ice imposes its own structure. It's a fluid moment, a transition between stable states, when the water column breathes deeply and redistributes itself. The bark of trees becomes more prominent and beautiful as leaves fall away, revealing textures and patterns hidden all summer. But bark is far more than decoration, it's a complex living tissue that protects, breathes, and communicates. The outer bark is dead tissue, but just beneath it lies the phloem, living cells that transport sugars from leaves to roots. In autumn, as leaves prepare to fall, trees create cork layers in their bark, sealing potential entry points for disease and insects. Some bark contains compounds that deter insect pests. Birch bark produces betulin, which has antifungal properties. The various patterns, the puzzle piece plates of mature pine, the papery layers of birch, the deep furrows of oak, aren't random but reflect each species' solution to the challenges of protection, growth, and gas exchange. As we admire autumn's bare trees, we're really observing countless adaptive strategies written in bark. Crows and ravens, those intelligent corvids, engage in fascinating autumn behaviors that suggest complex social learning. They cache food like squirrels, but with remarkable memory and, some researchers believe, awareness of being watched. Crows will create false caches if they notice other crows observing them, hiding food in one location then moving it after the observer leaves, but only if they themselves have stolen from caches before, suggesting they attribute their own knowledge to others. In autumn, young crows learn from their parents and flock members, acquiring not just cached food locations but the social intelligence of when to trust, when to deceive, and how to read the intentions of others. These birds live in complex societies, and autumn represents a critical learning period for juveniles, as experienced adults teach them survival strategies that go far beyond simple instinct. The last warm days of autumn sometimes bring out snakes for a final basking session before they retreat to their hibernacula. These late autumn appearances can be surprising, a garter snake stretched across a sunny rock on a November day when frost still glitters in shadows. This basking isn't frivolous, it serves a crucial purpose. The warmth allows snakes to complete digestion of their last meals before dormancy, and it may help trigger final physiological changes that prepare them for months without food or water. Snakes that enter hibernation with undigested food in their stomachs may suffer bacterial infections as the food rots internally at low temperatures. These final basking sessions are calculated risks. Emerging exposes them to predators and uses precious energy, but the thermal boost provides benefits that outweigh the dangers. They're reading the season carefully, taking advantage of every resource autumn offers. Autumn wind carries seeds in ways both obvious and hidden. The familiar helicopter seeds of maples, the parachutes of dandelions and milkweed, the winged seeds of ash and elm, all are adaptations for wind dispersal. But the efficiency varies dramatically based on design. Maple seeds spin as they fall, slowing their descent and allowing wind to carry them laterally. A single seed might travel several hundred yards from its parent tree. Scientists have studied these seeds to improve drone and helicopter design. Dandelion seeds are even more remarkable. Their feathery pappus creates a vortex ring above the seed, a bubble of stable, recirculating air that acts like a parachute. This allows dandelion seeds to travel for miles on even gentle breezes, remaining airborne for hours. Autumn wind is a transportation network, moving genetic material across landscapes, ensuring that individual plants contribute to populations far beyond their rooted locations. The ground beneath our feet freezes and thaws repeatedly during autumn's temperature swings, a process that creates unique soil structures. As water in soil freezes, it expands and pushes soil particles upward. Rocks embedded in soil gradually work their way to the surface through repeated freeze-thaw cycles, a process that can take years or decades but explains why freshly cleared fields seem to grow new rocks each spring. This same process creates patterned ground in Arctic and alpine regions, stone circles, polygons, and stripes formed by countless freeze-thaw cycles sorting stones by size. Even in temperate regions, autumn's freeze-thaw action contributes to soil mixing, bringing nutrients toward the surface and creating the loose, friable structure that plants prefer. Frost is a gardener, turning and aerating soil in ways that benefit spring growth. The ground is never quite still, it breathes with the seasons, expanding and contracting, rising and settling in rhythms tied to temperature and moisture. Owls cache food during autumn abundance, but unlike many animals that hide food and find it later by memory or scent, owls often simply wedge prey into tree forks or other locations and rely on freezing temperatures to preserve it. A great gray owl might kill several voles in good hunting weather, eating one and storing the others for later consumption. In cold climates, these stored meals freeze solid, remaining edible for weeks. This strategy only works where temperatures reliably stay below freezing, which is why it's more common in northern populations. The owl's adaptation isn't in food preservation technique but in opportunistic use of environmental conditions, letting winter itself be the refrigerator. It's a strategy that requires no complex caching behavior or spatial memory, just awareness of temperature and timing, taking advantage of the season's gifts. The last migratory birds passing through in late autumn are often the most weather-hardy species: dark-eyed juncos, American tree sparrows, and snow buntings that breed in the far north and consider temperate regions their warm winter destination. These birds time their migration to stay just ahead of serious winter weather, moving south in waves as cold fronts push down from the Arctic. They're built for cold, thick plumage, efficient metabolism, and behaviors that conserve heat. Juncos, sometimes called snowbirds, often arrive with the first snowflakes, their slate-gray backs and white bellies flashing as they forage in mixed flocks beneath bird feeders. Their arrival marks autumn's transition toward winter for many human observers, a reliable signal that the season is changing. These birds don't flee winter, they embrace it, just in locations where winter is manageable rather than extreme. Autumn phosphorescence in decaying wood reaches its peak as temperatures cool and moisture increases. Bioluminescent fungi, particularly species of Armillaria and Pinellus, produce a gentle green glow from their mycelium growing in rotting logs. This foxfire, as it's traditionally called, is bright enough to read by if your eyes are fully dark adapted, though it appears as barely a glimmer to eyes accustomed to artificial light. The biological purpose of this light production remains debated. It may attract insects that help disperse spores, or it may simply be a metabolic byproduct with no adaptive purpose. Walking through a dark autumn forest, you might see fallen logs glowing faintly, marking the locations where fungi are slowly transforming wood into soil. It's a reminder that even in darkness, even in decay, there is light, that decomposition itself can be luminous. The angle of autumn sunlight creates optical phenomena that are rare or invisible in other seasons. Sundogs, bright spots that appear on either side of the sun, occur when sunlight refracts through ice crystals in high, cold clouds. These are more common in autumn and winter when atmospheric conditions favor ice crystal formation. Autumn also brings crepuscular rays, those beams of sunlight that stream through gaps in clouds, sometimes called God rays, which are more visible when the sun is low on the horizon and atmospheric dust and moisture scatter the light. These aren't different rays but rather the same sunlight made visible by particles in the air. We see the architecture of light itself, the beams that are always present but usually invisible. Autumn makes the invisible visible, revealing the structure underlying what we normally take for granted. The very last flowers of the season are often the most determined survivors. Witch hazel blooms in November, sometimes even December, producing fragrant yellow flowers with ribbon-like petals that curl up in freezing temperatures and unfurl again when it warms, a strategy that protects delicate tissues from frost damage. This late blooming means almost no competition for pollinators, though few insects remain active. The flowers are primarily pollinated by small flies and moths that still fly on warmer autumn days. Witch hazel seeds take a full year to mature, and when they finally ripen the following autumn, the seed capsules explosively eject seeds up to 30 feet away, a ballistic dispersal that can be heard as a faint popping in quiet forests. This tree operates on its own timeline, blooming when others rest, fruiting when others bloom, following rhythms that seem contrary but have proven successful for millions of years. Beneath the leaf litter, salamanders are settling into their winter refuges, spaces beneath logs, inside rotting stumps, or in burrows deep enough to avoid freezing. Unlike frogs that can tolerate partial freezing, most salamanders must avoid ice formation in their tissues entirely. They seek locations where temperature remains above freezing but below their active range, a narrow window typically between 32 and 45 degrees Fahrenheit. Red-backed salamanders, the most abundant vertebrate in many eastern forests, gather in small groups in favorable microsites, sometimes dozens sharing a single rotting log. This aggregation may provide thermal benefits, or it may simply reflect the scarcity of truly ideal hibernation sites. These creatures breathe through their skin, requiring moisture year-round, so their winter refuges must maintain humidity as well as appropriate temperature. They're negotiating multiple requirements simultaneously, finding the rare locations where all conditions align. The soil food web shifts dramatically in late autumn as temperatures drop and surface activity slows. Bacteria that thrive in warm conditions become dormant, while cold-adapted species take over. Fungi, which generally tolerate cold better than bacteria, assume greater importance in decomposition processes. The balance of power in the microscopic world shifts entirely. Species that dominated summer's soil become inactive, while winter specialists emerge. Some soil bacteria form endospores, incredibly resistant structures that can survive complete desiccation, extreme temperatures, and even radiation, waiting years or decades for favorable conditions to return. Others simply slow their metabolism to near nothing, existing in a state of maintenance rather than growth. This invisible transition beneath our feet represents a complete changeover of the workforce that processes nutrients, controls pathogens, and maintains soil health. The soil in November functions fundamentally differently than the soil in July, though to the eye they appear identical. Hawks and other raptors that don't migrate south adjust their hunting strategies as autumn's abundance gives way to winter's scarcity. Red-tailed hawks shift from hunting in open fields where rodents are exposed to focusing on edges and sheltered areas where prey seeks cover. Their eyesight, already 8 times sharper than human vision, becomes even more valuable as prey becomes sparse and wary. These birds can see ultraviolet light, which means they can detect the urine trails that voles leave in grass and snow. The trails appear as glowing paths visible only to UV-sensitive eyes, leading directly to active burrows and feeding areas. As autumn vegetation dies back, these trails become more visible, giving hawks a unique advantage. Evolution has equipped them with senses we can barely imagine, allowing them to perceive a world of signals invisible to us. The last insects to succumb to cold are often the cluster flies and Asian lady beetles that seek shelter inside buildings and other structures. These insects engage in massive aggregations, sometimes thousands gathering in attics, wall voids, or other protected spaces. The aggregation itself serves a purpose. The combined body heat of thousands of insects creates a warmer microclimate, and pheromones released by early arrivals attract others, creating a positive feedback loop. These insects enter diapause, a state of suspended development where they neither feed nor reproduce, simply waiting out the cold months. Occasionally warm days will rouse them to brief, confused activity, crawling on windows or buzzing sluggishly, but they quickly return to dormancy when temperatures drop. They're neither alive in the fullest sense nor dead, but suspended between states, their biological clocks stopped until spring's warmth resets them. Late autumn rain has a different character than earlier autumn precipitation. It's often colder, more persistent, and arrives in gray systems that settle over the landscape for days. This rain penetrates deep into soil that's no longer protected by summer's transpiring plants, recharging aquifers and groundwater reserves that will sustain springs, streams, and wells throughout the following year. In regions with Mediterranean climates, these autumn rains mark the true beginning of the growing season, triggering the germination of annual wildflowers that will bloom in winter and spring. The rain also washes nutrients from decomposing leaves into the soil, completing the transfer of resources from leaf to earth. Without autumn rain, spring growth would be impoverished, dependent only on what nutrients remained from previous years. The rain is an essential courier, moving resources from one generation of plants to the next. Coyotes and wolves become more vocal in late autumn, their howls carrying farther in cold, dense air. These vocalizations serve multiple purposes: maintaining pack cohesion, advertising territory, and coordinating hunts. A single coyote can produce sounds that seem like a whole pack howling, using rapidly changing pitches and tones to create acoustic illusions. This deceptive chorus may make their group seem larger to potential rivals. The howling increases in autumn partly because young animals born in spring are now large enough to participate, their voices joining the family chorus for the first time. These vocal groups strengthen social bonds that will be crucial for winter survival when hunting becomes more difficult and territories are contested more intensely. The night air of late autumn carries these wild songs, communications in a language older than human speech, connecting members of a community we rarely see but that persists in the shadows of our settled landscapes. The last butterflies and moths of autumn include species that overwinter as adults, finding protected locations in bark crevices, under bridges, or inside caves. The underwing moths, large, beautiful species with colorful hindwings hidden beneath camouflaged forewings, spend winter as adults in a state of deep dormancy. Their antifreeze compounds allow them to survive temperatures well below freezing. When spring arrives, they'll be among the first moths flying, taking advantage of early flowers and the absence of predators. The morning cloak butterfly, dark wings edged in pale yellow, also overwinters as an adult, emerging on the first warm days of late winter to feed on tree sap flowing from wounds or early pussy willow catkins. These insects have traded the strategy of producing protected eggs for the strategy of protecting themselves, betting their survival on their own resilience rather than the resilience of the next generation. The bare branches of late autumn reveal birds' nests that were hidden all summer, intricately woven structures that endured rain, wind, and the weight of growing nestlings. These architectural marvels, now abandoned, demonstrate remarkable engineering. A robin's nest uses mud as mortar between layers of grass and twigs. An oriole's nest hangs like a woven sock, sewn to branches with plant fibers and animal hair. A hummingbird's nest, tiny as a walnut shell, is covered with lichen camouflage held in place with spider silk, which stretches as the nestlings grow. Most birds build new nests each year rather than reusing old ones, which may harbor parasites or have structural damage. These visible nests are monuments to parental devotion, structures that served their purpose and are now returned to the ecosystem. They'll decompose slowly, providing nesting material for mice, insects, and next year's birds, which will cannibalize old nests to build new ones. Nothing is wasted, everything circles back into use. The very last leaves clinging to trees in late autumn often tell stories of individual survival and adaptation. Oak leaves, especially, practice marcescence, holding their dead leaves through winter, particularly on younger trees. Scientists believe this evolved as protection for tender terminal buds from browsing deer and harsh weather, or perhaps to drop nutrient-rich leaves in spring when they'll decompose faster and benefit the tree's own roots rather than nourishing competitors. Each species has its own leaf drop timeline, refined through millions of years. Beech trees also hold leaves through winter on young growth. These persistent leaves rattle in winter winds, creating sounds that were once the only music in winter forests before evergreens spread widely. They're not mistakes or failures to complete autumn's work, but deliberate strategies, leaves held for purpose even in death. Millipedes and centipedes retreat deep into soil and under logs as autumn ends, seeking stable temperatures and moisture. Despite their similar appearance, these creatures represent very different evolutionary strategies. Millipedes are detritivores, gentle consumers of decaying plant matter, with 2 pairs of legs per body segment, moving slowly like living waves. Centipedes are predators, venomous hunters with 1 pair of legs per segment, moving with startling speed to capture prey. Both are ancient lineages that have persisted for hundreds of millions of years, far longer than mammals or flowering plants. As they settle into winter dormancy, their following instincts older than autumn itself, their ancestors were among Earth's first land animals, crawling from ancient seas onto barren shores long before the first trees existed. They've survived countless mass extinctions, and they'll survive this winter, as their kind has survived countless millions of winters before. The crystalline structure of frost that forms on cold autumn mornings is actually a form of ice crystal growth that follows mathematical patterns. Frost doesn't simply freeze randomly but grows in branching, fractal patterns, each crystal a miniature tree of ice, with 6-fold symmetry reflecting the hexagonal structure of water molecules. Hoarfrost, the delicate feathery frost that decorates every surface on cold, humid mornings, grows as water vapor in the air transitions directly to ice without becoming liquid first, a process called deposition. Each crystal is unique, shaped by the precise temperature and humidity conditions during its formation, yet all follow the same basic hexagonal geometry. This regularity arising from chaos, this order emerging from randomness, reflects fundamental physical laws. The beauty of frost isn't accidental, it's geometry made visible, physics expressed in ice. Voles and mice dig extensive tunnel networks beneath autumn's leaf litter and snow, creating highways invisible to surface observers. These subnivean spaces, the zone between ground and snow, maintain surprisingly stable temperatures, hovering near freezing regardless of air temperature above. A mouse can remain active all winter in this protected environment, feeding on seeds, roots, and bark, rarely if ever emerging into the harsh surface world. Their tunnels can extend for hundreds of feet, connecting feeding areas, nest sites, and escape routes. Predators like foxes and coyotes can hear mice moving in these tunnels and pounce through snow to catch them, a hunting technique that looks like play but is deadly serious. These hidden spaces beneath snow are entire ecosystems, hosting not just mammals but insects, spiders, and even some species of ground-nesting bees that remain somewhat active through winter in the relative warmth of the subnivean zone. The silence of late autumn is not truly silence but rather a different soundscape. With leaves fallen, sound travels differently through forests, farther in some ways, as there's less vegetation to absorb it, but also with different quality. The acoustic environment changes entirely. Bird songs are largely absent, replaced by the calls of ravens, crows, and the occasional woodpecker's drumming. Wind sounds different through bare branches than through leaf-covered ones, a rattling, clicking sound rather than the susurrus of summer foliage. Water sounds become more prominent as other sounds fade, the gurgle of streams, the drip of snowmelt, the crack of expanding ice. Animals that remain active use this changed acoustic environment to their advantage, listening for prey or predators across greater distances. The forest hasn't gone quiet, it's speaking a different language, one of winter rather than summer, of survival rather than growth. Turkey vultures, those ungainly but magnificent scavengers, are among the last birds to depart northern regions in late autumn. Unlike most raptors, they rely heavily on smell to locate carrion. They can detect the scent of ethyl mercaptan, a gas produced by decaying animals, from over a mile away while flying. As temperatures drop and decay slows, finding food becomes more difficult, triggering their migration. They travel in groups called kettles, riding thermal updrafts to gain altitude with minimal energy expenditure, then gliding south for miles before finding another thermal. Some individuals travel thousands of miles from Canada to South America. These birds, often unfairly maligned, perform essential ecosystem services, cleaning up carcasses that would otherwise spread disease, recycling nutrients, and maintaining ecological balance. Their departure signals that autumn's abundance of death, fallen animals, insects, the casualties of migration, has been processed, the cleanup complete. The Earth itself tilts more dramatically away from the sun as autumn progresses toward winter solstice, creating the shortest days and longest nights of the year. This tilt, 23.5 degrees from vertical, is responsible for seasons themselves. As the northern hemisphere angles away from the sun, solar energy arrives at an increasingly oblique angle, spreading the same amount of energy over a larger area and passing through more atmosphere. The result is not just less daylight but weaker sunlight, even at noon. The sun hangs low on the horizon in late autumn, its rays slanting rather than direct. This astronomical reality drives every biological adaptation we've observed: migration, hibernation, leaf fall, dormancy. Everything traces back to this tilt, this orbital dance between Earth and Sun that's remained constant for billions of years. The seasons aren't Earth's moods but its geometry, physics expressed as the passage of time. Lichens, those partnership organisms of fungus and algae, actually grow more in autumn and early winter than in summer in many climates. Summer's heat and dryness stress them, causing dormancy, but autumn's cool moisture activates growth. They absorb water directly from rain and fog, swelling and turning vivid green or yellow or orange within minutes of wetting. In this hydrated state, the algal partner photosynthesizes while the fungal partner mines nutrients from its substrate, rock, bark, or soil. Lichens are extraordinarily slow-growing. Some large individuals may be centuries old, but autumn represents their prime growing season. They're also incredibly resilient. Lichen species have survived exposure to the vacuum of space in experiments, enduring radiation and temperature extremes that would kill virtually any other organism. These humble, Overlooked organisms clinging to rocks and trees are among Earth's toughest survivors, and autumn is when they truly thrive. The very last warmth stored in ponds, lakes, and even soil is released gradually through late autumn and early winter, moderating temperature extremes for nearby areas. Water has a high specific heat capacity. It takes substantial energy to warm it, but it also releases that heat slowly when cooling. Large bodies of water act as thermal buffers, keeping nearby land warmer in autumn and cooler in spring. This is why vineyards and orchards are often planted near lakes. The moderated climate extends the growing season and protects against late spring frosts. On a smaller scale, the soil itself retains summer's warmth for weeks after air temperature drops, allowing roots to continue growing, microbes to remain active, and burrowing animals to find refuge. This stored heat, invisible and often unconsidered, is a gift from summer to winter, a buffer against the shock of seasonal transition, a gentling of change that makes survival possible for countless organisms. And finally, autumn teaches us perhaps its most important lesson, that letting go is not loss but transformation, that endings enable beginnings, that death feeds life in ways both literal and profound. Every fallen leaf becomes soil, every migrating bird carries ecosystems on its wings, every sleeping bear trusts in awakening. The season shows us that nature doesn't resist change but flows with it, adapting, transforming, finding beauty in transition. Autumn is not the dying time but the preparing time, the season of faith that what is released will return, that what sleeps will wake, that the wheel will turn again. As we watch the last colors fade, the last leaves fall, the last birds depart, we witness not an ending but a promise, that beneath the apparent death, life persists, patient and certain, waiting for its moment to emerge again into light and warmth and the eternal return of spring. Rest now, as autumn rests. Sleep, as the seeds sleep in soil and the bears sleep in their dens and the trees sleep standing sentinel over the quiet land. Trust in the turning of seasons, in the wisdom of cycles older than memory, in the promise that darkness always gives way to dawn, that winter always yields to spring, that what appears lost is merely hidden, waiting, gathering strength for the grand return.